So the first question here is, why are solids rigid? So if you want to look at why are solids rigid, first understand how the solids are arranged. The solid particles are arranged in a three-dimensional shape. So as we can see, each of these solid particles, however their arrangements are, they're all touching each other. So in this case, the constituent particles have two things. One is a strong attractive forces because they're very close to each other, and the other one is they have very less interparticle distance. So if you look at these two diagrams, where though the solid state, the arrangement of the particles in the solid state are different, they still have very less interparticle space, which means each of these atoms really have no distance between them, and they have a very strong attractive force. So in this case, solids cannot move freely. What else can they do is they can only vibrate about their mean positions. Wherever they are, the only movement that they can have is vibration. And therefore, all solids are rigid in nature. So that's how you can answer this based on the question asked. Next, in the question 1.12, it says, why do solids have definite volume? The theory of this question is also similar to the previous one. We're going to talk about the interparticle distance and the strong attractive forces which are responsible for the way the particles are arranged, and because of that, they can only vibrate about their mean positions. They cannot move freely. Therefore, solid particles are rigid as well as they have a definite volume because of all this. So for 1.1 and 1.2, the answer is the same. There's no difference in it. Now the next one is, classify the following compounds as amorphous or crystalline solids. They've given certain compounds here. One is polyurethane, then they have naphthalene, you have benzoic acid, we have Teflon, we have nitric potassium nitrate, we also have cellophane, PVC or polyvinyl chloride, fiberglass or copper. So for this question, before we move into finding the answer, which one is going to be amorphous, which one is going to be crystalline, we learn a little about amorphous and crystalline solids, and then we will move into. Now, when we learn the chapter, we all know that we have two types of solids. One is crystalline, amorphous. The same thing we're also doing in practicals in chemistry, where we are given a crystalline or an amorphous solid and asked to identify the salt. So we actually know how they look practically also. So here, under crystalline solids, what do we get? We get elements or we get compounds. Right? But what about amorphous solids? They are normally polymers or mixtures. Now, what are polymers? Whenever we look at plastic, we look at fiber, we look at rubber or glass, all of these are coming under polymers. Alright, so here when we are talking about how to classify a certain list of compounds or items under crystalline or amorphous solids, look at this particular classification. It becomes easier for us to classify each of this. So here, when you're looking at polyurethane, the term poly itself means a compound is under polymer. So if it's a polymer, then it has to be an amorphous solid. Now the next one is naphthalene. Naphthalene is a crystalline compound. It is a compound. Naphthalene is an aromatic compound, so it has to be crystalline. Now the next one is benzoic acid. Again, these are all salts that are there in our lab itself. Therefore, they are crystalline in nature. They are compounds. Then we have Teflon. Teflon, we all know these are all polymers. They're all plastics. So these come under amorphous substances. Then we have potassium nitrate, which is crystalline. These are all salts available in the lab. So they're classified as crystalline solids. Cellophane is again a polymer. Therefore, they're classified as amorphous solid. PVC is also a polymer, polyvinyl chloride. Therefore, they're amorphous. Fiberglass is amorphous again. They're again coming under polymers. And your copper is a metal or an element. Therefore, it's coming under crystalline nature. So you'll be able to classify whether a given compound is amorphous or crystalline based on this particular classification that you know. Crystalline solids, you generally have elements or compounds. Amorphous solids are polymers or mixtures. Now the next one is 1.4 question. The question says, refractive index of a solid is observed to be the same value in all directions. Comment on the nature of the solid. Would it show cleavage property? So here, when we learned about differences between amorphous and crystalline solid, refractive index was one of the things that was telling us the definition for anisotropy and isotropy. Under that, we learned that these physical properties, when they are measured along a particular direction, then it would give a certain value. If it's measured in a different direction, depending on whether they're crystalline or amorphous, they would give different values. So based on that, we are going to learn right now. But remember one thing, that refractive index is a physical property. So it is in the presence of light, which means it's a physical property. So when we try to measure them in different axes or different directions, say I'm trying to have a compound, I'm trying to measure refractive index along x-axis. It is giving me a certain value. If I'm measuring along y-axis, based on the question, it has to give me the same value. If I'm measuring along z-axis, it is supposed to give me the same value. That is the type of question that we're focusing on right now. All right, so here if a physical property has the same value along different directions, then such kind of a nature is called as isotropic nature. And we learned under properties that if a solid has isotropic nature, such kind of solids are amorphous solid. So the first question here, it is clearly, we have cleared it out, that comment on the nature of the solid, it is amorphous solid because they are isotropic, which means if physical properties measured along different directions will have the same value. Now the second question clearly asked here is, would it show a cleavage property? Now what do you mean by cleavage property? Any salt that you take in lab, if it is, say, if it is say it is in a ball shape or something, when you cut it, if it is a crystalline solid, it would give you a clear edge surface. But for example, if I'm taking a chalk and I'm doing that, whenever you can also try this in school, take a chalk and try to break it or try to cut it. When you cut it, what happens? It is not going to give you an even surface. If you see closely, you will find that the surface are quite uneven, which means there is no proper cleavage property. Amorphous solids belong to such kind of compounds where when we cut it using a sharp tool, it does not give a clear edge. So here amorphous solids, when cut with a sharp tool, they do not give a regular surface, they will give irregular surfaces. Therefore, amorphous solids do not show a cleavage property. So till here it answers your first question. The second question is talking about the cleavage property. Basically, when you cut them, what happens? Are they going to show any cleavage property or no? Now the next question is, classify the following compounds in different categories based on the nature of intermolecular forces operating on them. And there are certain examples given to us, which is potassium sulphate, tin, benzene, urea, ammonia, water, zinc, sulphide, graphite, rubidium, argon, silicon carbide. Now here in this classification, if you need to know what belongs to where, first you need to know what are those classifications. Otherwise, it is not going to help. So based on intermolecular forces, we had learned a table itself. Like in one of the videos, I had explained it. If you have not seen it, please go ahead and see. There are a few videos behind where I've explained clearly in detail about this particular chapter, each topic. So please go through it, then you will be able to answer these. So before we solve this question, we'll first see what are those intermolecular forces on which solids are classified. So here we have ionic solids, metallic solids, and we also have covalent and molecular solids. All right, so we have 4 types of solids here: ionic, metallic, covalent, and molecular solids. 4 types of solids are there. Ionic solids meaning our constituent particles are going to be ions. If you're talking about metallic solids, your constituent particles are going to be metals. If you're talking about covalent solids, you're going to talk about your constituent particles being atoms. Or if you're talking about molecular solids, your constituent particles are going to be molecules. So depending on that, you can identify by looking at these examples. So potassium sulphate, they are ionic solids because you can get potassium ion and sulphate ion, ionic solid. Tin is just a metal, therefore they are metallic solid. Benzene is a molecule, therefore they are molecular solid. Similarly, urea, ammonia, water, they are all molecules, so they are classified under molecular solid. Zinc sulphide, you can get Zn2 plus separate and sulphide separate, therefore they are ionic solids. Graphite, we all learned last year that graphite, when we look at the structure itself, the bonding there is covalent, therefore they are covalent solids. Rubidium is a metal, therefore they are metallic solid. Argon comes under noble gases, they are molecule by itself, therefore they are molecular solid. Silicon carbide also we learned last year, therefore they are called as covalent solids. So if you can identify the nature of these compounds or elements, you'll be able to classify them based on the intermolecular forces between them, and you will have your answers right. So before you try to solve such questions, better know what these classifications are, so it becomes easy for you all to answer such questions. Next is question number 1.6. The question says solid A is very hard electrical insulator in solid as well as in molten state and melts at extremely high temperature. What type of a solid is it? So here the question clearly gives you properties of a particular type of a solid. We need to identify from that what is the nature of the type of the solid that we're having. So here the properties say it is very hard. We all know solids are hard in nature. For a few exception cases where solids are soft. The next property says electrical insulator. Now what's the meaning of an electrical insulator? Electrical insulator meaning it is not going to conduct electricity at all. Insulator meaning a property where it doesn't conduct electricity. Like for example, if you take your cellophane tape. You tie the wires with the cellophane tape, it is not going to help and conduct electricity. So there are certain electrical metals which are electrical insulators, which means they don't conduct electricity in solid phase, as well as if you're trying to melt them, molten state also, where even at very high temperature it is not going to conduct any electricity. So these are a few properties given to us. From that we need to identify. So if you look at the table where we learnt about molecular solid, ionic solid, covalent solid, metallic solid, we all know the properties that are coming from there. Now when you're talking about, say for example, metals which are they are very hard. Now if you see from that metallic solids, most of them are softer ones. So metallic solid is completely out, because under metallic solid there are a few which are soft. Then when you look at ionic solids are hard, but they are brittle. But the conductivity characteristic feature says that it will conduct electricity in the molten state. So ionic solids are also not an option. You are left out with metallic solid, but metallic solids, they say they are conductors in solid state as well as in the molten state. So it is definitely not going to be a metallic solid. So the only option that you are left with is covalent solid. So here for this type of question given to us, the type of solid here is a covalent solid. So out of these four, the answer is covalent solid. So we need to understand the properties. Only then you'll be able to actually tell what type of a solid is for so and so question. Alright, now question number 1.7 reads, ionic solids conduct electricity in molten state but not in the solid state. Explain. So for this, I would like to take an example of sodium chloride, which is the simplest ionic solid that we can talk about. Now we all know, even in lab also, or simple thing, sodium chloride is a salt. If table salt, you can say, if you look at your salt that's there in home, we all know that the nature is crystalline. So if they are crystalline, that means when you try to melt them, it can give you sodium ions and chloride ions. So here in solid state, the sodium atoms and chlorine atoms are tightly held by strong attractive forces in solid state, right? Here, but when they are in a molten state or you try to melt them, these will turn into ions, and the ions are free to move, and the interattractive forces between them are the least. Why? Because you're trying to move away from each other. Now when that happens, the attractive forces between them will be the least. Therefore, Na plus and Cl minus ions formed will start conducting electricity in the molten state. So it's a very basic type of questioning that is asked in this. So that means it should be easy for you all to answer also. Alright. Now, question number 1.8 reads, what type of solids are electrical conductors, malleable and ductile? Now in this case also, it clearly reads that you have three properties: electrical conductors, which means they are conductors of electricity; malleable and ductile are those properties of metals that can be beaten into sheets or drawn into wires. Alright, so those characteristic feature can be easily given by metallic solid. Alright, so that is the answer for question number 1.8. Now the next one is question number 1.9. It says, give the significance of a lattice point. And before we know what is the significance of a lattice point is, try to understand what is a lattice point. Now, if you look at a cube, each corners of these cubes have some dots. They are nothing but lattice points. You get the geometry of a cube is when you join those lattice points, you get the entire unit cell. Right? So here lattice points can be atoms, they can be ions, or they can be molecules also. These dots that you see can be atoms, they can be ions, they can be molecules. But in a diagram, how are we trying to represent them? They are represented as a point. When these points are joined together, they are going to form an entire lattice structure or a crystal lattice. Now that is the significance of a lattice point. That's why we need it. If we don't have a lattice point, we cannot study about the BCC or FCC or a simple cube or packing efficiency. Nothing of these can be learned. So lattice point may seem a small thing, but its significance is big. Alright. Now, question number 1.10, it says name the parameters that characterize a unit cell, which means when I take a unit cell, what other different parameters can I take into consideration? This is just a simple example of, say you've met someone new, but for you to talk to them or for you to discuss something with them or approach them, first you need to know basic mentality of that person or a thought process of that person, or at least know who that person is. Same thing here, when you're studying about unit cell, you need to know what are the basic parameters in that particular unit cell. Now, how are you going to come to that conclusion? For that, you can take a simple cube. Now, when you look at that cube, what happens is you have different edge length in this case. Now, a cube necessarily doesn't mean it's going to have the same angle, the same. We have learned 7 different parameters, primitive unit cells in this chapter in the start itself when we learned. So that means to say a unit cell need not be a cubic shape always. It can be hexagonal, it can be monoclinic, it can be rhombohedral, which means the angle can be different, the edges can be different. So here, when you look at a cube, it can have one of these edges which are the smallest, which is given as A, another long edge which is given as B, and the one going vertically upward, which is the height of it, which is the C. So that way we will have 3 edges A, B and C. Now each of this will have a different bond angle depending on how long the edges are. So we will have between B and C, you will have a bond angle which is alpha. Between A and C, you will have a bond angle which is beta. And between A and B, you will also have a bond angle which is gamma. So that way you will have 3 different angles, alpha, beta and gamma. So therefore, we will have 6 parameters when you look at a unit cell. So this way you will be able to identify what are the different types of alpha, beta, gamma or A, B, C in a particular type of a unit cell, which is not necessarily always a cube. We have also learnt about 7 primitive unit cell in the very start of the chapter. Alright. So the next question is 1.11. It says distinguish between hexagonal and monoclinic unit cell. And the second question is face-centered and end-centered unit cell. So in this, we will look at the diagram of each of this to understand what it is. So the first question is distinguish between hexagonal and monoclinic. So this is a diagram of a hexagonal. You can see that there are different edge length and there are different angles also. So let's look into it in detail. So here, when you look at it, when you have these angles which are here, the edge length which is here, this is A, B and this is C. So A and B, both the edge lengths are the same, but these are not equal to C because C edge length is the longest. So they are not the same. Now similarly, when you look at the bond length, here you have alpha and you have beta. Both of these are 90 degree. But when you look at gamma here, which is a longer, bigger angle, gamma is 120 degree. Now when you try to compare the structure with the monoclinic unit cell, they're very different. Now, under monoclinic unit cell, if you clearly see, you will know all the edge length are different because you can see 3 different edge length here. This is A, this is B, and the one going vertically up is very longer than the other one. So A is not equal to B, which is further not equal to C. What about their angles? Here, alpha and beta, both of these are not equal to each other, but alpha and gamma are not equal to each other. This is alpha and gamma are not equal to each other, but Your alpha and beta here, both of them are 90-degree upward. Right? So here, if you see the difference between them, they're way different when compared to each other. Hexagonal has a different bond angle and edge length. Monoclinic has a different bond angle and a edge length. Now the second question is face-centered and end-centered. So look at the diagram. Now face-centered meaning what? If you're sitting in a room and listening to this video, you can see that around you, you have 4 walls. One in front of you, one on your right, one on your left, and one behind you. So you have 4, and one above and one below. So total, how many surfaces do you have? 6 surfaces. On the center of each of this surface, you will find an atom in the center. Now that is a face-centered unit cell. How is it going to be different to an end-centered? End-centered diagram, if you see, if you're sitting in a room, the wall facing you and the wall behind you, those are the 2 ends of a crystal. Or you can say the wall that is there above you and the wall that is there below you, that is the roof and the floor. Those are the 2 ends of a unit cell. So you're considering any 2 ends when you're talking about end-centered unit cell. So both are different, they're not the same. Though we have an atom in the center of the face, for a face centered, on all the centers of the face you have one atom. But when I talk about end-centered, 2 ends, any 2 ends you can consider. Either your right and left, top and bottom, or front and back. Any 2 ends you consider, that is an end-centered unit cell. Alright. Now, the next one is 1.2. Here it says, explain how much portion of an atom located at the center or body center of a cubic unit cell is a part of its neighboring unit cell. So here, first one, when you look at it, firstly you need to understand what is that particular atom am I going to mean about. So for this particular, the one that's marked in pink color is 1 unit cell. I'm going to talk about that one atom of that unit cell which is shared among other 8 unit cells. How is it 8? On top layer I have 4, bottom layer I have 4. So this particular atom is shared among all other 8 unit cells. So that way, for a simple cube, I am sharing that one atom to 8 other unit cells. So it's going to be 1/8 of a contribution per unit cell. This one atom is shared with 4 other unit cells on top and 4 other below, which means totally surrounding that particular atom. Now the second question says body-centered unit cell. So if you see body-centered unit cell, only one atom in the center is there that is belonging to that one unit cell. It is not shared with any other. So the contribution is only 1 contribution per unit cell. Alright. And the next one is 1.13. It says what is the two-dimensional coordination number of a molecule in a square close packing. Now I've done a detailed video about this in one of my videos in the previous ones. You can just open that and find out what do you mean by this square close packing or two-dimensional square close packing and all of that. But still I will just go through it roughly by showing you a diagram. So here if you see this arrangement, if I had only one layer here below, that means it was a one dimension. But now I'm going to have repeated layers one above the other. So this is one dimension, this is my second dimension. So this is a two-dimensional square close packing. Now in this case, I want to know what is a coordination number. So I've taken a random sphere over here that's in the center. How many atoms are touching it? I have one here, one here, one here, and one here. So total there are 4. So the coordination number of any atom in a two-dimensional square close packing is 4. You just see how many atoms are touching a particular atom in that entire arrangement. That way you're going to identify what is a coordination number. Alright. Now, this question clearly says a compound forms hexagonal close pack structure. What is the total number of voids in 0.5 mole of it, and how many of these are tetrahedral voids? So before we move into the video, into the question, you need to know how many tetrahedral voids and how many octahedral voids are generally there. So number of tetrahedral voids are 2n and number of octahedral voids are n. Now what is it n? N is nothing but number of particles. So first we'll find out what is n. So n, number of moles, we all know that n number of moles is nothing but number of particles divided by Avogadro's number. This we have all learnt it in mole concept also. Number of moles is equal to, in terms of Avogadro's number, it's going to be number of particles divided by Avogadro's number. In this case, number of moles we know, which is 0.5 mole in the question. Na is a constant. We need to find out what is N. When we substitute the values here, N is equal to 3.011 10 raised to 23 after we cross multiply them. So now that we know what is N, the question we need to find out is number of tetrahedral voids. Now number of tetrahedral voids are going to be 2n. So 2n meaning 2 into this 3.011 into 10 to the power 3. 23. Now when you do that, you get 6.022 10 to the power 23. That is the number of tetrahedral voids here. So that is the answer for which says number of tetrahedral void. The question, there was a second question that says how many of these are tetrahedral void. We calculated. But there's one more question. What is the total number of voids in 0.5 mole? We need to know total number. So now what we will calculate here is, it says total number of voids is nothing but what is the total number of tetrahedral void plus the total number of octahedral void, which we'll find out here. So that will be equal to 9.033 10 to the power 23. Where if we get this number of octahedral void? Because number of octahedral void is n only, and we already find out. We have already found out here. So when you substitute it, you will get what is the total number of voids for 0.5 mole of the compound. Alright. Now the next question is, a compound is formed by two elements M and N. The element N forms CCP and atoms of M occupy 1/3 of tetrahedral void. What is the formula of the compound? So first thing, let's get a few information from the question. We have two elements M and N. Of that, N will occupy the CCP. CCP can also be FCC or HCP. So when you have that, we already know that the Z value or number of atoms per unit cell is nothing but 4. So that is done with N. But what about M? M is occupying 1/3 of tetrahedral void. So therefore, tetrahedral void is nothing but 2 into Z. Alright. So here, because 2 into Z is how? Because the number of tetrahedral voids are 2n. So here we can say 2 into Z, which is equal to 1/3 is occupied by tetrahedral void. So 1/3 into 2 into Z is 4. So we're writing, because it's a HCP, we're going to write it as 4 here. When we simplify this, we'll get 8/3. Now this 8/3, for the ratio, when we see 8/3 is by M and 4 is by N. So when we put it as ratio, it's going to be 8/3 is to 4. Multiply this 3 over here, you get 8 is to 12. Make them into the simple ratio, you get 2 is to 3. Therefore, the formula of the compound is M2N3. Alright, so this way it's easy for us to calculate the formula of the compound if you know how to get a few information from the question directly. So the next question for the video is 1.16. Which of the following lattices has the highest packing efficiency? Simple cube, BCC or FCC? So as we have learned in the entire chapter, we have learned a complete derivation of packing efficiency for simple cube, BCC and FCC or HCP. So these are the basic structures of these unit cells. Now from this, we learned packing efficiency from the derivation for simple cube to be 52.4%, BCC 68% and FCC 74%, which is for HCP. So we generally say that more the percentage of packing efficiency, more is going to be the more is going to be the packing efficiency of that particular unit cell. So in this case, HCP has the highest packing efficiency as the percentage of that unit cell is the highest. So here the answer is HCP. Now the next question is 1.17. Now here the question says an element with molar mass 2.7 10 to the power 2 kg per mole forms a cubic unit cell with edge length 405 picometer. If its density is 2.7 into 10 to the power 3 kg per meter cube, what is the nature of the cubic unit cell? So from this question, what are the values given to us? We are given with M, which is the molar mass, which is 2.7 10 to the power 2 kg per mole. We are given with A value, which is the edge length, that is 405 picometer, but we need to convert this to meters. So it will be 405 10 raised to minus 12 meters. The next one is density, which is 2.7 10 raised to 3 kg per meter cube. We are asked to calculate the nature of the unit cell, which means Z value. So from the density formula, we know density, we know molar mass, we know what is A. We can then cube it. Na is going to be a standard value or a constant value. So from this entire equation, we need to calculate what is the value of Z. So once we substitute the values in with these equation, for D we have 2.7 10 raised to 3. Then we have the value of A, which needs to be cubed. Then we have the value of Na, which is a constant, 6.022 10 raised to 23. And the last one we have is the molar mass, which is 2.7 10 raised to 2. So when we calculate all of this, that Z is coming to 4. So here, when Z is equal to 4, the nature of that particular unit cell is an FCC, because when we calculated the number of atoms per unit cell for FCC, Z value was 4. So in this case, with these values, the nature of the unit cell is a face-centered cubic unit cell. Now the next question is question number 1.18. What type of a defect can arise when a solid is heated? What physical property is affected by it, and in what way? So totally 3 questions. First, we'll try to understand what do you mean by when a solid is heated? What happens? So if you see here, there is positive, negative ion, which are denoted in these orange and gray dots, which these are arranged perfectly. Therefore, this is a perfect crystal. But in the next one, it is showing that when we heat it, one positive ion and one negative ion is not there. It is missing from an entire lattice. So here, when a solid is being heated, the constituent particle can leave the lattice side and it can create a vacancy. So here, if you see, positive, negative ions are missing and a vacancy is created, which is a vacancy defect. So that answers the first question. Now the next one says which physical property is affected by it. Now whenever this happens, we look at 2 physical properties. One is the volume, the other one is mass. Now in this case, the volume is going to remain the same. There is no change in it. But what happens to mass? The mass is going to reduce because these have moved out. So the mass is going to decrease. When mass decreases, the density of that particular lattice is also going to decrease. So 3 questions are answered here. First one is what happens when you heat it. Second is which sort of a physical property is affected. We know density. In what way is it affected? The density is going to reduce. Now the next question is question number 1.19. What type of a stoichiometric defect is shown by ZnS and AgBr? So before we jump into trying to analyze what it is, let's see what are the stoichiometric defects that we have and what does stoichiometric defect itself mean. So stoichiometric defect meaning the stoichiometry or the ratio of particles are not disturbed. No matter what you do, the ratio is not being disturbed. They are also called as intrinsic or thermodynamic defect. Now under stoichiometric defect in our syllabus we have learned 2 types. One is Schottky defect, the other one is a Frankel defect. Now Schottky defect meaning these are observed in cation and anion of comparable sizes, which means the cation and anion can be of almost similar size. But Frankel defect is observed where they have a huge difference in the size. Now based on the size, we can tell whether ZnS is going to show Schottky or Frankel, or whether AgBr is going to show Schottky or Frankel. So here we can say that because the difference between the silver and bromine atom is not very big, thus they are of almost comparable sizes, they can show Schottky defect. And the other one, of course, Zn is a much bigger one and sulphide is a smaller one. Therefore, they have a huge difference in their cation anion size. Therefore, this will show Frankel defect. So zinc will have a smaller size, sulphide is much larger. Therefore, zinc sulphide will show Frankel defect. Schottky defect is shown by AgBr. Now we have also learned one of the classic examples that AgBr can also show Frankel defect. So both can be shown by AgBr because they have a little bit of difference in size, but they are also comparable sizes. So that answers your question number 1.19. Now next one is question number 1.20. Explain how vacancies are introduced in an ionic solid when a cation of higher valency is added as an impurity in it. Now I've done a detailed video about this. It's nothing but impurity defect. So here I have a lattice of NaCl, but at one point I have another atom of a higher valency sitting there. So what is happening? So here what we're going to do is consider crystallization of molten NaCl with small quantities of strontium chloride. Now remember, Na is with a +1 charge, strontium is with a +2 charge. So during the process, what will happen? Some of the Na atoms are going to be replaced with a strontium atom. So to replace one strontium atom with sodium atoms, you need to remove two sodium atoms because the valency of sodium is, the oxidation number of sodium is Na +1, whereas strontium is +2. So two sodium atoms need to come out to sit to accommodate one strontium atom. In order to maintain neutrality, that entire process needs to happen, where two sodium atoms are lost to accommodate one strontium ion. Now when this happens, what happens? At one point there is a vacancy created, which is a cationic vacancy. Therefore, the number of cationic vacancy produced will be equal to the number of strontium ions that are introduced into the lattice. So if there's one strontium ion, that means one vacancy will be created. So this is going to answer your question number 1.20. Now your next one is 1.21, which says ionic solids which have anionic vacancy due to metal excess defect develop color. Explain with the help of a suitable example. Now this also had explained in detail in the video where I spoke about your defects in one of the videos. Now here it says sodium chloride crystals, when they heated, what happens is sodium atom is going to come out. Now when sodium atom comes out, what will happen here? An electron will sit in place of that sodium atom. Now what is happening to this particular electron when it is heated? This electron is going to absorb light of a suitable frequency and it is going to give color to the flame. Now that color is the reason why you get barium. For barium you get apple green, for strontium you get crimson red. The reason you get a flame is because of this one electron. When it is heated, it gets excited. Now this particular center where an electron is there and that's responsible for a color, that center is called an F center, or it's called as Fibre center. Alright, so this is going to be the detailed explanation of question number 1.21. Now the next question is 1.22, which is the last question in the chapter. A group of 14 elements is to be converted into N-type semiconductor by doping it with a suitable impurity. To which group should this impurity belong? This also I done an entire detailed explanation for this. When you're trying to dope it with another group to form an N-type, which means you need to have negative electrons. So here you need to have more number of electrons in order to get N-type, because N-type meaning negative type of an semiconductor. So in this case you need to dope it with a group 15 element in order to get an N-type semiconductor. So I hope this video is helpful to all of you, because I have tried to answer all possible questions that are there in this entire chapter. And I hope it's clear. If you have any further suggestions, please don't hesitate to put it in the comment box. I have seen a lot more of suggestions that are coming up in the comment box, and I will be doing a video of all of that very soon. So I'll see you in my next video. Until then, stay tuned.